This is the second in a video series explaining different types of exponential growth and decay problems. This is a half-life problem, and it's a pretty standard half-life problem, really just trying to get back in the swing of things that we did in pre-cal for those of you who took pre-cal last year and are reviewing it for calculus, which I think is why I'm making this video. So anyway, just to remind everybody, carbon-14 has a half-life of 5,730 years. So if you find a bone, you can actually essentially analyze the percent of the carbon-14 remaining. And the whole concept of the half-life is that every 5,730 years, half of the C14 decays. And so anyway, it's constantly decaying, continuously decaying, which means we can use that PERT formula, or the more generic form, y equals C naught times e to the kt, or y equals n times e to the kt. We can use that formula to model this continuous decay of the carbon-14 and try to solve the problem. Okay, so again, our key here is 35% remaining. Half-life is 5730 years. So let's try to model what's going on here. So you're actually going to need two equations here. You've got your y equals C naught e to the kt power. The first thing you want to focus on is the half-life. Okay, so we know that the half-life would be the number of years. That's 5,730. Okay, we actually need to figure out what the growth rate, it's not actually a growth rate, it's a decay rate. We need to find out what that percentage is. And it breaks down very slowly. It takes 5,000, almost 6,000 years for it to break down to half. So it's going very slowly. It's going to be a very small decimal. Will be a negative decimal because it's dividing. We're getting smaller over time. You can do this various different ways. You could say, notice it didn't say you had this many grams and then it broke down to it didn't say you start out with 16 grams, now you have 8 grams left or something like that. It literally doesn't matter. As long as you have a ratio in which your starting value breaks down to half, it'll work. So you could have 100% breaking down to 50%. You could have 1 unit breaking down to a half unit. It doesn't matter. You could have 10 units breaking down to 5 units. Your choice, okay? That being said, the first thing you're going to do, because we're trying to figure out what k would be here in this equation, and so we're really trying to solve this. Well, the first thing you're going to do is get rid of that leading coefficient in front of the e, because if you're going to work with logs, you want to have a base, an exponent, and a result. You don't want this fourth thing that's a constant out here. You want to get rid of that constant first. But look what happens. When I divide by that leading coefficient, we're going to end up with 0.5 is equal to 1 times e to the 5730k. So this is the same thing as if I just started out with 1 unit breaking down to 0.5 units, which is why I just go ahead and do it that way. But again, it doesn't matter as long as you've got the correct ratio there. Now be careful. Don't do 100 and then have it break down to 0.5. Do 1 and 0.5 or 100 and 50 or 20 and 10, but make sure that the output is half, okay? Not that you're doing one thing with percents and the other thing with whole numbers. Anyway, we can solve this. So it's an exponential equation, it involves decay. It's going to be a log base e. Remember, the log base e is a natural log of 0.5 is equal to the exponent, because logs are always exponents. And anyway, ln of 0.5 here is going to be approximately negative 0.693. Again, you should leave that in your calculator. You should probably write lots of decimal places if you're really going to do estimating, which I would not encourage you to do. Anyway, I'm going to divide both sides by 5730 here. I am keeping this full decimal in my calculator. And anyway, when I divide there, I end up with a k value that's about negative 1.209 times 10 to the negative 4th power, okay, which is going to roll the decimal place 4 positions. Okay, so that's my k value, and again, it's going to be negative because this is decreasing, and negative exponents mean you're dividing by something instead of multiplying by something. And again, it's going to be a very, very small decimal because it's doing it very slowly. It's taking it almost 6,000 years to break down to half. So anyway, we can back up here now, and actually we pretty much just take all of this out of here. So my k value, my decay constant is about negative 1.20 968 times 10 to the negative fourth power. That means I can move the decimal 4 places left. K is going to be approximately negative, what is that? It's going to be 3 zeros, right? 1001 20968. Again, I'm leaving it in my calculator. I'm just going to write down a few things here so you can kind of see what I'm doing. 1, 2, 3, 4 decimal places there. Yeah. All right, so the follow-up question then is we want to know how old a bone would be that has 35% of the carbon-14 remaining. Well, now we know the K value. We're now looking for a year. And the nice thing is the K and the T are both part of the exponent. This is going to set up almost exactly the same as before. So we can say we want 1 unit. So you've got C naught times e to the K T power. Okay, C naught times e to the KT power. We want 1 unit to break down to 0.35 units. Or again, we could have 100% break down to 35%. Just make sure that this is 35% of that. Okay, same kind of thing. We can solve. Of course, I don't really need the 1 there. This is going to be a log base e, which is a natural log of 0.35, and it's going to be equal to the exponent, which is this whole big decimal here, which again, I'm really keeping in my calculator. And anyway, ln of 0.35 is approximately negative 1.0498, and that's equal to negative 0.001200968t. I'm going to divide both sides by this decimal. Again, really keeping everything in my calculator here. Okay, and when I do that, I'm going to get that T is approximately 8,678 years, 0.504. Again, AP wants you to round to 3 decimal places. You know, they may ask you to go to the whole year, or it could be multiple choice, and they're doing whole years or something like that. Now, you should think about the problem a little bit. Only 35% remains. That means it's gone through more than 1 full half-life series, because that would have knocked out, 1 cycle of half-life would have knocked out half of it, and that would take 5,730 years. So we've knocked out more than 50%. We expected, in fact, once you're down to 50%, if you take half of that, that's 25%. We're not too far off of 25%. So yeah, we'd actually expect it to be having gone through, you know, 2.5, you know, at least 1.5 cycles, something like that. So this 8,000 makes a lot of sense, and you should be able to use a little bit of common sense to check at the end and make sure your answer stacks up okay. So hopefully that all looks familiar. Hopefully that'll kind of come back pretty easily to you as we continue to work back through some of these log review problems.